What I'm going to talk about today is a technique called multilevel modelling, which is a statistical method for looking at populations with structure. So let me explain what I mean by that. So what I mean by population structure and dependencies is the idea that if you read the first, not that you would choose to read it necessarily, but the early chapters of a statistics book often assume everything is random, people selected at random and so on, but assume that we have randomness and independence. And sometimes that makes sense. If you have the natural sciences, for example, it makes sense that things could be random, so you get things like white noise and so on. And it keeps statistical theory simple, which is why it's often in the beginning of a statistics book, but really it's not very useful for looking at many situations. So when you're looking at people or social data, and lots of other data sets as well, lots of other types of application, we can't assume things are random. So people are not raffle tickets when, the population's got structure. If you went to Fallowfield in Manchester, you're more likely to see two people that you see in the street are more likely to be students than two people, each from a different part of Manchester. There's kind of clustering in the population. So if we just assume everyone's random and independent, then we're keeping things simple, but we're not realistically reflecting what's happening in real life. So we want to take into account the fact that living in the same area, people have got something in common, say the pollution, the water quality. Going to the same school, you've got the same educational regime, you've got the same school buildings and this kind of thing. So things are in common, and so people cannot be regarded as independent units as if they were raffle tickets. And so some more examples: pupils in schools, individuals in areas, or workers in organisations. So each of these, you can see, have sort of different levels. So pupils in schools, for example, you could think of pupils at level 1 and schools at level 2. Similarly for individuals at level 1, areas at level 2, or workers at level 1, and organisations at level 2, and lots of other applications you could think of. So a brief history of the method then. Well, actually the problem of single level analysis and cross-level inference, I'll explain what cross-level inference is in a second, was coined by somebody called Robinson in the 1950s when he wrote a paper in Political Science where what they did was to take the percentage of people voting for a particular party and then looked at the percentage of people from particular ethnic groups and did a correlation at the area level and then made inferences about what people would vote given their ethnic group. But basically what they did was did the analysis at the area level and then made inferences about the individuals. So this is why I use the phrase cross-level inference. And the problem there is if you do the analysis of area-level data and assume it applies to individuals, you're running into problems coined the ecological fallacy, which is that group-level correlations, for example, or regression equations do not automatically apply to the individuals that comprise those groups. So really what we need to do is to take the individuals and the groups into account. And people like Stan Openshaw demonstrated in human geography in the 70s and 80s the problems of the ecological fallacy and all sorts of, you can basically come to all the wrong conclusions if you analyse data at one level and make inferences at another. Then in the 1980s there was a lot of discussion of school league tables and school effectiveness, and of course school league tables were originally, and quite often still are, based on single level aggregate data. So you've got the percentage of pupils getting a certain number of GCSEs in a school. But of course it's not the school itself that takes the exam, it's the pupils. So we need to take into account variations, not just by schools but by the pupils within the schools. So the problems here are that if you just rely on a single level analysis, you'd lose some of the information about variation, and that's really crucial. And there are key papers and books by Aitken and Longford, Harvey Goldstein and Steve Raudenbush on this topic. And then what happened sort of from the 80s was that there were advances in computing power and estimation methods such as IGLS, which you won't remember, but it's called iterative generalised least squares, and these could be fitted with specialist software. So we have things like RCL, HLM, and then this great long string of developments that became MLWin. So some of you may have heard of MLWin, which is a piece of software for doing multi-level analysis that's free to academics, and I'll explain where you can find that later. So the original focus in multi-level was on hierarchical structures, for example, pupils in schools. Also, another really important application of multi-level modelling is in longitudinal analysis, and it's particularly useful because it doesn't have to have the same number of observations at each occasion. So if your blood pressure was taken at 4 times a year, spring, summer, autumn, winter, and if somebody wasn't present for one of those occasions, multi-level modelling can still look at a longitudinal analysis, taking into account the data that's there. There don't have to be observations for everybody at every time point. So this is an advantage of this method over things like repeated measures. And more recently, multi-levels moved on to non-hierarchical situations, such as cross-classified models, where basically groups overlap. And more modern methods, such as Monte Carlo Markov chain and ever-increasing computing, means that we can fit realistically complex models to the population. We don't regard the population as independent. We don't say that they are. We don't sort of assume that people are like raffle tickets. We actually realistically take into account that people that belong to the same area, go to the same school, have something in common, which surely is a good thing if we're looking at substantive research questions in the social sciences and beyond. So a non-exhaustive list in sort of social statistics. I've seen applications in education, including longitudinal studies of, say, reading tests and so on, in human geography, in health, in more recently in social network analysis. So it could be your friendship network becomes the group that you're a member of. And in psychology, these can be used for all sorts of interesting ideas, including multivariate and latent variable analysis. So I've basically talked about 2 levels so far. Another extension that we can think of is more levels. So instead of just having individuals in areas, we could have individuals in households in areas, or pupils in classes, in schools, in regions. Now, of course, whether you can fit this kind of model will depend on the data that are available. It might be that you don't have household level data, but if you have these different levels, this enables you to look at several levels and look at the variations in things like self-assessed health measures, educational scores, and so on. Another extension is people not at level 1. So when I was first learning about multi-level, I thought, oh, okay, just remember that the person is at level 1, but that's not always true. So, for example, in longitudinal studies, the occasion that the measure is taken is actually level 1, and then the person is level 2. So this example I gave you with blood pressure measurements, if it was spring, summer, autumn and winter, that occasion would be level 1, and then the person would be level 2. But then, of course, you could have that the person lived in a particular area, so you could extend that. And we can also think about multivariate studies with several different Y variables, so that we could capture latent variables. So if we have lots of test scores that include something with a mathematics or maths type component or physics and so on, we could perhaps look at underlying measures of numeracy or intelligence, this kind of thing. So they're useful for latent variable analysis as well. So these realistically complex structures, even more things you can do. These are very recent developments. Cross-classifications, basically 2 pupils that sit next to each other in the same class might actually each live in a different area of a city, whereas 2 people that live next door to each other might each go to a different school. So if you were looking at area effects and school effects on people's progression through education, then you would have these 2 overlapping groups. We could use a cross-classified approach. And so that substantively the influence of the neighbourhood and the school on the educational performance of the individual. So we've got these 2 levels that would overlap, and then another level of the individual. But this is real life. This is realistically complex. We're not making it complicated because we want to. It's reflecting what happens in real life with the method. So this becomes a very powerful substantive quantitative methods tool. And finally, multiple membership models. Good example is that during the course of secondary education, some pupils attend more than one school, possibly because their parents move, and so some pupils are therefore members of more than one group. And you can actually say that the person went to school 1 for the first 2 years, and then school 2 for the next 7 years or something. So you can actually put weights in to for the analysis to reflect how long they spend in each group. And this again becomes very powerful substantively, because in reality people do move schools and so on. Some people stay at the same school, some people move, but this multiple membership model can take that kind of idea into account. But let's not go too complex today. Let's focus on the two-level situation for the rest of the talk. So it's time for some diagrams, I think. So a simple two-level hierarchy. Now this is simplified in the sense that I've only got 2 schools there, and in total I've only got 7 pupils, 3 in the first school and 4 in the second, and that's just so that it fits on the slide. In reality you would have a bigger data set, perhaps with 20, 30, 60 schools, something like that, and in each school maybe you've got 20 or 30 or more pupils. But you can see here that in this school 1 you've got 3 pupils. Now each of those pupils might take an exam, and they won't all get the same mark. Well, it's very unlikely that they would, so there'll be variation between their exam score within the school, but then you could then say on average they get a particular mark, so that there would be then a school average which you could compare with the next school. So this structure allows you to say, well, the school average is the average of those 3 exam scores, but that might differ from the school average at the next, but you've still taken into account the variation within. Whereas if I went for a single level analysis, I would ignore that variation within the school and just say that all I need is the school average. This is saying, no, you don't just need the school average, you need the individual pupil score so that you can look at the variation within as well as the variation between the schools. So in this simple two-level hierarchy, we've got 2 schools and 7 pupils, and at level 1 is the pupil, which, and these might take a test score, each of them, and then level 2 is the school. So you can see this is the simplest example of multi-level with 2 levels. So of course we then have a multi-level situation, and the variations in the exam score or whatever you were measuring could then be looked at. And of course you could then, instead of having schools here, you could have areas or organisations and workers and so on. So you can apply this to lots of different situations. So what data do we need to allow us to fit these kind of models? Well, we need individual units. That sounds a bit scary, but it just usually means people with group indicators, which would, so if this was pupils, this would just be which school does this pupil go to, which area does this person live in. And usually that data can be found certainly for more big geographic areas. So sometimes for reasons of confidentiality you can't get really small geographical areas, but you can get data for pupils in, or for people say in Manchester, and compare that with Sheffield and so on. So you've got areas and you've got individuals, or you've got pupils and schools. You'd need one or more response variable, or you could call that a Y variable or a dependent variable if you like. And in general we'd need more than one person per group to allow us to look at the variation within groups. And also in general we'd expect to have at least 10 groups. 20 or more would be even better, because if I just go back to that previous slide, then if we only have 2 groups, we could just use dummy variables to compare. Some of you have used dummy variables presumably, and you could just compare one group with the next if you just have a small number of groups with a so-called fixed effects analysis. What the multi-level analysis is a random effects analysis, which is technically a bit more complicated. I'm not going to go into detail about that, but it basically it's a more efficient way of dealing with lots of groups than it would be to have lots and lots of dummy variables, and it's got more potential for looking at particular things that might answer your substantive research questions. So let's suppose we had data for 4,000 pupils in 60 schools. What could we actually do with that information? Well, and let's also assume that we've got an exam performance at 16 that they've done recently, and also we know how they did when they were 11, these pupils in schools. And let's suppose we've also got some other explanatory or X variables, or you might want to call them independent variables. So for example, the gender of the pupil, the age of the school buildings, and the percentage of pupils on free school meals. Now these are interesting explanatory variables because the gender obviously applies to the pupil. The age of the school building is obviously something about the school, and the percentage of pupils in the school that are on free school meals is something about the pupils that's then been aggregated to the school level. So what the multi-level modelling framework allows you to do is to consider measures that are made at the individual level, or in this case at the pupil level, at the school level, and also information that's been aggregated to the school level. So it's a really powerful framework in that situation. Let's suppose what we want to do ultimately is relate how well people are doing now in their exam or test to how they did when they were 11, taking into account these school conditions and the gender of the pupil. What could we do? Well, we could aggregate the exam scores at 11 and 16 to the school level, so that instead of having 4,000 exam scores, we would have 60 pairs of school means. And then we could do a single level analysis. But we know that this is a problem from what I was saying earlier, because we'd run into this ecological fallacy problem where we would do our analysis at the school level and then want to make inferences about the pupils. So this would be a problem of cross-level inference. So we don't like that idea. We could just ignore the school and say, well, if there's too many of them, I can't put that many dummy variables in my model, so ignore it. But this seems a bit daft to ignore the school, because surely the school is a crucial part of the educational process by its very definition. So we don't like this because we're ignoring the context. Each pupil goes to a particular school. So what we then would like to do, of course, is to use a multi-level model that allows us to look at the different levels simultaneously, i.e. the pupil level and the school level in this example. And technically we don't require all these long list of dummy variables, and we can also do interesting things with the multi-level model. So we can say, for example, is the relationship between how well you did at 11 and how well you do at 16, is that relationship the same across all the schools, or is it sometimes a stronger relationship, a steeper line if you like, or is it always the same kind of relationship? So this is substantively very interesting, because then if you're looking at things like value added, you can start to say, well, what was the value added by going to that school versus this one? And also, again, I won't go into the technicalities, but basically, if you've got different numbers of people in the different schools in this example, that's taken into account with something called shrinkage. But basically, you don't need to know what that is. It just takes into account how much information you've got for each school in this case, or generally for each group. So if you've got just 2 people in a group, that is taken into account compared with the next group that might have, say, 100 or something. So that's very important. And so I think this is probably the most technical slide without any algebra on it, but I think it's useful to say that multi-level models are sometimes called random effects models because the groups themselves are actually regarded as a sample. So in our pupils in schools example, we actually regard the schools as a sample as well as the pupils being a sample, in fact a random sample. And because of that we can make inferences about groups not in the sample. So if we only had half the schools in Manchester taken at random, we could still make some kind of inference about progress in the relationship between previous and current exam score. But if we had all the groups, then we can still regard the population as a sample. So it goes a little bit sci-fi where you sort of say that the population you've got is some kind of realisation of a process in space and time. But let's not get into that in too much detail. The idea is that you can use this in lots of different situations. And sometimes the structure is not actually of interest. Sometimes you've had to use a multi-stage or cluster sample to collect the data, and you're not actually interested in any of the parts of that. You just want to take into account the way in which the data were collected in the way in which you analyse it. So in that case we can use multi-level models as a model-based approach to reflect the way data were collected, to reflect our sampling design when we analyse it. And so what I've done now is there's a slide of algebra and then a graph. So if you don't get the algebra you might get the graph, but you might get both. So it's useful to just think about what we would do in a multi-level modelling situation. So let's suppose we've got this data. Let's just think about the 4,000 pupils in the 60 schools, and let's just think about, first of all, the variable for the exam score that they've just done. So that would be our y variable. And in the multi-level model, we'd know that this was a multi-level because it would be a yij, so it would be y for pupil I in school j. And we could first of all fit something called a variance components model. The reason why we do that is to see how much variation there is between exam score within the schools and between the schools. So this model doesn't even have any x variables in it. So why would we fit it? Because before we fit any explanatory information, how much variation is between pupils and how much variation is between schools in a particular example. So graphically, it looks like this. So some of you might prefer the graphs to the equations, but here, each of these colours that hopefully you can see at the back and the front represents a different school. So this kind of lilac line here, that's the school average, that horizontal bit, and those dots are the scores that the pupils actually got. So the variation for the pupils within the school is the distance, or the amount that these little dots move around that line, which of course is the school average. And then the variation between schools is the difference between these horizontal lines. And the reason why the lines appear all over the graph is because some pupils here didn't do very well in this school, typically didn't do very well. We've got variation here between pupils and between schools that we can measure, which is why we fit this. And then what we say is we want to relate. This is what we would do if we didn't do a multi-level model. So if we did a simple regression model, then we would just say, I'm going to ignore the school, I'll relate how well the pupil does in the exam now to how well they did before. So this is the exam score they've got when they're 16, this is the exam score they got when they were 11, and we say, well, I can relate how well you do now to how well you did then. But this simple regression model, by very definition, doesn't recognise the fact that pupils go to school, so particular schools, so it would just be one line with this slope for the whole population, and I think I've got a graphic for that. So this would be single regression, would just be that line, and you would be saying, I can explain everything about how you did before in your exam and how well you do now, just with one line, and I don't need to take into account the schools. So we don't really like this because this is just a single level model that just produces one line, where we know in fact that all these different colours represent the fact that pupils actually go to different schools. So what we really want to do is to combine that idea of fitting a line with this idea that that the differences around the average for different schools. So what we do is we take the variance components model and we take the simple regression model, we put them together, and this gives us something called a random intercepts model, which basically fits that regression line of how you did before to how you do now, but moves the intercept of that line according to the different school. So I'll show you what that looks like on a graph. On the graph we can now see that, yeah, the overall line is still there from the simple regression, but what we've now got is the line for each of the schools. So you can see that all of those lines for the different schools, again the lilac one is down here and is parallel to the overall line, because what we've done is move the intercept, which is why it's called a random intercepts model, because the intercepts can move up and down, but the slopes of the line are the same as the overall. So what we're saying here is the relationship between previous exam score and current exam score is the same. The actual relationship between the two is the same, but the intercept is different. So the slope of the regression is the same, but the actual place where it crosses the axis is different for each school. And we could then say that for any particular school we can then measure, well, how much higher than the average is that intercept. We can do it for a particular school. So for each of the schools in our analysis, we can actually get a measure of how different our school is from the overall average, which is quite powerful. So for this one, for example, this school 1 has got a higher intercept. This is saying that on average pupils are doing better in this school on the exam score now. Then the next one is the opposite, where this one is moving below the overall average. So in this school, pupils are not doing so well on average. So this is quite powerful. And then what we can then do is to say, well, is the relationship the same in each of the schools? And we can start to say, well, it could be that in one school there's a very shallow relationship between how you did before and how you do now. In the next school it's a very marked relationship. So we can start to look at whether that is the same with more complicated models. And I don't want to get too much into the technicalities of the algebra, because these will then be available on the website and with my commentary. But what this also allows you to do when you've got multi-level is to add level 2 variables. In this case, these would be school level variables. So for example, as well as having how you do now in an exam versus how you did when you were 11, you could add the percentage of people on free school meals, this aggregate measure based on the pupils aggregated to the school level, or something about whether the school was built in the last 50 years, so something about the school itself. So you can add information at the pupil within school level, this IJ level, or, in this case at the school level, it's just got a J subscript here to represent that. So this is, don't worry if you don't get the algebra straight away, but you get the idea, hopefully, that you can add information at different levels that you allow for in the model. What that also gives you then is a powerful framework for combining data, so that if you had some survey data that included particular areas that you could find information about from the census, you could bring information in from the census to augment your survey. So it's really quite powerful. And just finally, again, don't worry about the algebra, but just think about how useful this is substantively. In this one, I'm just focusing on this extra thing I've got in the model, beta 3 x1ij times x2j, which sounds very complicated, but in words, what I'm saying here is I can look at the effect of previous exam score in the context of the percentage of free school meals in the schools. So I can say, in a school where there are lots of free school meals, is the relationship between previous exam score and current exam score different than it might be where there are hardly any free school meals? So you can start to look at the conditions of the school in terms of the population and so on, with a cross-level interaction. And now, so that's basically taking information from one level and interacting it with information at the next. That's very powerful substantively for lots of reasons, because again, you're thinking about things in context. So this has got a really powerful substantive use. But I think it's time for a few more graphics. So what we get in multi-level modelling, I'm not going to tell you about the technicalities, but we get a measure of how correlated people are within groups. So earlier on I used an example that if you walk down the street in Fallowfield and looked at two people, there would be a higher probability that those two people were students than if you just took one person from one part of the city and one person from the next. So we get clustering in the population. And so we can think, how correlated are people with respect to particular qualities? So if it was pupils in schools, we can say, in a particular school, how similar is one exam score to the next? Is the correlation between them? And so we get this measure, which is rho, which is the same letter we use for correlation in sort of classical situations. But this is the correlation between particular individuals in groups with respect to something that you want to measure. And the higher the correlation, the more clustering, the more similar people are within groups. And so here we have a small value of rho, so there's a little bit of clustering, a little bit of movement from the overall line. So just remember that graph, and then look at the next one, which has got a high value of rho. This is saying, look, the schools are really moving away from the overall relationship. And if we just fit a straightforward single-level regression rather than a multi-level model, we're really ignoring a crucial feature of the population, and it really would matter. So if there's some strange, if rho was actually 1, if the correlation was 1, then every pupil's score would lie exactly on the regression line for that school. But more importantly, I think, is that comparing a situation where you've got, say, a high value of rho here, if you ignored the schools in this analysis, you'd get the wrong inferences. So substantively, it wouldn't make sense to ignore the schools, but statistically, it would also give you the wrong answers. If in a different situation there was no clustering, there was no correlation between the values of one thing in a group to the next, then actually you just end up with a sort of random cloud of dots, and then the overall line, because there's no similarity of people in groups, the groups in that case wouldn't matter, and you could then use a single level analysis. But that's very rare. And really what you'd want to do is to use the multi-level model, the variance components model, to measure that value of rho. So we can get that measure of rho from the variance components model. And we can go on with this just very briefly. So when you have, if you fit a single level model, so let's just again think about this pupils in school example. What you're really saying is, I can summarise everything about all the schools in Manchester, let's say, with one line, which seems a little bit of a strong assumption, doesn't it? But that line would just have one slope and one intercept. Once you go to a random intercepts model, then you're saying, well, I think there should be a separate line for each school in Manchester, say, and each of those different colours would be a different school. The overall line is still in there, is that bold black line in the middle, but now you've got lots of different intercepts, sometimes below, sometimes above. But look at those lines, they're parallel, so there's only one slope, because all that's changing here is the intercept. Then, of course, if you have a random slopes model, then not only can the intercepts change, but by definition also the slopes. And you may have a situation where a high intercept is associated with a steep slope and a low intercept is associated with a shallow slope. And you can actually measure these kinds of things using the multi-level analysis. So that's one pattern. So what this would be really interesting for would be to say that if, let's take the pupils in schools example, if we had some low achieving pupils, the extent of variation between all the schools is that distance there, which is a lot less than for the high achieving previous test score pupils, where there will be a lot of variation. So substantively this is very important for looking at, does the difference between schools stay the same at different values of x, or does it change? So again, really powerful. You know, where are the biggest differences between schools? Is it for pupils that did well in the past or didn't do so well in the past? Of course, we could have the converse of that. So here, the real differences are for pupils that didn't do well in the past, and the less differences for pupils that did really well. And sometimes you end up where there isn't any obvious correspondence between the lines, the intercepts and their slopes. But still, you can find this kind of thing out with the multi-level approach. And we can also get other useful measures from the model, like the residuals, that basically, without going into technical detail, because I'm coming to the end of my talk, but this would enable us to make fair comparisons of schools, where we've taken into account not just the school means, but also the variations of the pupils within the schools, and also taken into account the amount of information we've got for the different schools. So, just very quickly, this school here, in fact, there are only 2 pupils in the data set. So the confidence interval for that group is very wide because there isn't very much information. Whereas some of these with smaller confidence intervals are based on much more pupils. Or many more pupils. So this is making fair comparisons, say, between schools or whatever it was the groups in your analysis, taking into account individual and group level variations. So just to conclude then, what is multi-level modelling? Well, in my view, it's a way to investigate variations and relationships for variables of interest, taking into account population structure and dependencies, even if those things are not of primary interest. So even if all you want to do is to take into account the way that the data are collected, this is useful. But more often, you would be interested in the structures. So, for example, pupils in schools or geographical examples. And then you can really investigate relationships within those structures in great depth, with lots of possibilities for testing social theories with these quantitative methods. So I think it's a flexible framework for testing sophisticated social, or indeed any other theories, looking at individuals in context, and that could include the context of change over time. These slides will obviously be on the website very soon, but I won't go in. I'll just tell you the titles of the slide. So there's a slide about the different software packages. Okay, so there's a slide that's about useful web resources. And I'll just mention the one at Bristol, if you want to very, very quickly jot that down. Maybe I'll leave it on that slide actually. But that resource at Bristol is fantastic for finding out things about multi-level modelling, and indeed getting hold of the MLWin software. If you have an ac.uk email account, you can basically get a copy for free. So that's useful. And I will stop talking.
Thank you, Mark, very much indeed.